So let's look at the dot product. A vector is basically a line segment. It's a line segment in 2 dimensions, it's a line segment in 3 dimensions, it's a line segment in any dimensions at all, and as I said to you yesterday, that's the beauty of using vectors, is it doesn't matter which dimension is, the rules and all the properties are going to stay the same. Okay, so what do we know about the dot product? If we've got 2 vectors, neither of which is the 0 vector, then we know that the dot product of the two is the magnitude of u times the magnitude of v times the cosine of the angle in between the 2 vectors. Theta could turn out to be acute or obtuse, it just depends on which direction the different vectors are going. Now, if one of those vectors is 0, so one of those vectors is the 0 vector, just like in normal maths, well, anytime you multiply by 0 you get 0, so the same happens in the dot product. If one of those vectors is the 0 vector, then the answer will be 0. Probably more correct to say the 0 vector. But then there was this other way of finding the dot product. In 2 dimensions, we got the x values, multiplied them together, the y values, multiplied them together. So logically push it through to 3 dimensions now, we can say, oh, now we'll also get the z values and multiply those together as well. So different properties from the dot product. Because it's times the cosine of theta, and we know theta goes between -1 and 1, that means our dot product must go in between minus the multiplication of the 2 magnitudes to positive the multiplication of the 2 magnitudes. So the dot product should lie in between those values. We know we can do it in any order. U dot v will be the same as v dot u, very similar to multiplication. Now I've written down the one for 2 dimensions here, but for 3 dimensions we just add in the z1 squared. But the point is, u dot v is still the magnitude squared. Doesn't matter how many dimensions we've got. Remember, you're not actually expanding with multiplication, you're expanding with the dot product. So a dot, the u plus v, would be a dot u plus a dot v. So the dot product, not multiplication. It also means we get something like this, which looks like the difference of 2 squares. And it is, when you look at the answer, but it comes from the fact that we've got u dot u, which we know is the magnitude of u squared, minus v dot v, which is the magnitude of v squared. Constants, well, we can always factorise constants out, so I could do the dot product of u dot v and then multiply by that constant. That's a valid way of doing it. And we also know that if the dot product is equal to 0, that tells us that the 2 vectors are perpendicular to each other. The cosine of 90 is 0. If u dot v turns out to be either plus or minus the magnitude, then we know the 2 vectors are parallel. We know they have to be parallel. Why? Because cos theta, what's it telling us? It's either going to be 1 or -1, which means the angle was either 0 or 180 degrees. So they're either going in the same direction, if it's positive, or they would be going in opposite directions if it was negative. So let's prove this little expansion, that indeed a dot b plus c is the same as a dot b plus a dot c, and prove it true for 3 dimensions. So I'll rewrite my vectors in component form. The first one becomes a1i plus a2j, a3k, and I've done a similar thing for the b plus c. Now remember, when we expand these out, what am I getting? Remember, when we find the dot product, we get the x value times it with the x value. So in this case we're going a1 times the b1 plus c1. Then we get the y value, multiply it with the y value. So a2 times b2 plus c2, and then finally a3 times b3 plus c3. To expand that all out, but then I'm going to recombine them in a different way. So I'm grabbing all of those, and I've got a1b1 plus a2b2 plus a3b3, and then in the other one I've got a1c1 plus a2c2 and a3c3, because that now is a dot b for the first one, and the second one would be a dot c. It proves that particular relationship. Well, let's prove that these ones are perpendicular. Okay, let's get the dot product. So multiply the x value with the x value, the y value with the y value, and so on. And yep, that turns out to be 0. If the dot product is 0, the vectors are perpendicular. Now, you remember yesterday I said slope really becomes meaningless in 3 dimensions, because vertical rise over horizontal run, what on earth are we talking about? Because depending on how we orient the three-dimensional space, what's rise, what's run? But they all make angles with the different axes. And that's what this one's saying. It's going to make an angle of alpha with the x-axis, an angle of beta with the y-axis, and an angle of gamma with the z-axis. If I bring this back to two dimensions, let's just have a look at something here. There is a line, or a vector. It makes an angle with the x-axis. It also makes an angle with the y-axis. If I was to look at cos squared alpha plus cos squared beta, what would it equal? Well, I could rewrite beta as 90 minus alpha. And of course, cos of 90 minus alpha is sine. We end up with cos squared plus sine squared, which we know is equal to 1. So cos squared alpha plus cos squared beta is equal to 1. So that now brings us back to this question, where what we're going to be asked to do is actually prove that that same idea is true in three dimensions. So the cos squared of alpha plus the cos squared of beta plus the cos squared of gamma is equal to 1. So I'm going to let our vector be this, AI plus BJ plus CK. Let's have a look at u dot I. It has to be equal to A, because remember, I is the unit vector in the x direction. It has coordinates, if you like, of 1, 0, 0. That would be the vector. To do the dot product, I would multiply the x value with the x value, so A times 1. The y value with the y value, so B times 0. And then the z value with the z value, so C times 0. So u dot I is equal to A. We know that to be true. But we also know that I could have written it as the magnitude of u times the magnitude of I times the cosine of the angle in between, which we've been told is alpha. But the magnitude of I is 1, it was a unit vector. And the magnitude of u I can find with the square root of a squared plus b squared plus c squared. So I now have a new expression for the dot product. But of course they've got to be the same thing. I can now rewrite this and find a value for cos squared alpha. Now I could do exactly the same thing for beta. The only difference is I'd have b squared on top instead of a squared. And I could do exactly the same thing for gamma, but I would have c squared on top. So if I add the three together, I get a squared plus b squared plus c squared over a squared plus b squared plus c squared, which of course is 1. And there's our result. Now let's have a look at this one from last year's HSC. We were given this triangular pyramid and we've told certain things about it. So L's the midpoint of AB, M's the midpoint of AC, N's the midpoint of AD, P is the midpoint of CD, and Q is the midpoint of BD. So there's lines going everywhere here. Oh, Jesus, I forgot about R being the midpoint of BC. There's another point. They've told us that the vector AB we're going to call B, the vector AC we're going to call C, and the vector AD we're going to call D. We have to show that the vector LP can be written as a half of negative B plus C plus D. So we need to get it in terms of these other three vectors that we've been told. So I guess the question is, how do I get from L to P? What's another way I can get from L to P so I can get these vectors in there? So the path I chose to take was I went from L to A, which would be the negative of the vector AL. Then I went A to D, because I've been given those two. But that means I now have to go from D to P. But hang on, they told me that DP was a half of DC, because P was the midpoint. Okay, so now I've got it. Because A, if you like, is the origin. The three pieces of information they gave me all are coming from A. So I can think of B, the position vector coming from A, and so on. Well, that means I can sub in for AB the B, I can sub in for AD the D, and the DC would be head minus tail, C minus D. Tidy that up, I get the result that they want. Okay. Whoa, look at this one. We didn't have to go and work it out. So they told us the next two. Well, MQ we could have done a similar way, and it would be that expression, and they've also given us NR as well. But they want us to prove this huge result. I got myself an expression for LP squared, because I'm going to need it, the magnitude of LP squared. And so, well, I know that would be the same as the vector LP dot the vector LP. Now, why do that? Well, In part I, they just said show that LP was this. So I kind of figured that, yeah, that's probably I'm going to use this. So that's where I'll start, by using that. So I've got a quarter of. Now I expand the whole thing out. But remember, when I'm expanding, it's actually the dot product I'm doing, not multiplication. So negative b dot negative b would be b dot b, which I know is the magnitude of b squared. And similarly, I get my c dot c, which is the magnitude of c squared, and a d dot d, which is the magnitude of d squared. And in the other one, I get twice all of these minus b dot c and b dot d and c dot d. The only difference between LP, let's go back, there it is. In the LP, it was the b that was negative. In the MQ, it's the c that's negative. And in the NR, it's d that's negative. So if this is my expression, and notice how only one of them in the second parentheses is now positive, then I just have to say, well, this would be the same, but now in the second parentheses, it's going to be the BD that is the positive. And in the NR squared, it'll end up being the B dot C that is positive. So I now have these three things. So 4 times that. So if I add those three things together, but also multiply by 4, which is nice because it gets rid of the quarter for all of them, I'll end up with 3 lots of the magnitude of b squared plus 3 lots of the magnitude of c squared plus 3 lots of the magnitude of d squared and minus 2 these dot products. Okay. Well, that's where I went, okay, where do I go from here? Maybe I'll now look at the other side. Let's see if I can show it's the same thing. Now the other one was magnitude of AB squared. Well, we know that, that's magnitude of B. Magnitude of AC is magnitude of C. Magnitude of AD is magnitude of D. BC, I'll go head minus tail. BD, I'll go head minus tail. CD, I'll go head minus tail. Okay. But when I'm squaring these, what I'm really saying is C minus B dot C minus B and so on. Expand those out now. Okay, I'll get another magnitude of C squared here and magnitude of B squared, but I'll have minus twice the, well, for want of a better word, product. Well, it is product, it's dot product. And each of those parentheses become the same thing. Tidying that up, and we get the same result. So, all right. So 5C is now using our dot product, but using it in 3 seconds.